Sure, Santosh. Okay, Atharva, just let me know if my voice trails off or you don't hear it loud enough. Okay.
Right now it's loud and clear.
Okay, that's good. Okay, welcome everyone. I think we'll get started with the Stellarium session. So I would like to personally welcome you all to the refresher course, the faculty participants who are joining for the refresher course 2022, and also the student participants who are joining for the summer program. Welcome, and I hope this. Now, this particular session is going to be a lot more casual, so you need not wait till the end to ask any questions. As long as it's relevant, you can stop me at any point and you can ask me questions about something that I might have just explained and you didn't understand or would want more clarification about. So if you had read the abstract, this is going to be about the Stellarium software. I'm sure a large fraction of you would be aware of it to various extents at this point. You must have at least heard about it or seen a demonstration somewhere before. Some of the repeat participants of the refresher course, I hope you enjoyed the session last year and you were able to implement some aspects of it in your pedagogy. If you did use it in the previous year, do let us know by emailing us how your experience was and what are the things that you would want to be changed or added in the future for um, to teach to the students particularly. It would be always good to hear feedback. Okay, so the tone of the presentation today is going to be similar to how it was last year, especially for the repeat ones. I should clarify that. This is to keep in mind the people who are joining for the first time and would like a fresh introduction to Stellarium. We will, however, try to touch upon a few of the advanced features of Stellarium or some of the advanced activities in the next session. So there would be something useful to build up on what you already know for the people who already are aware of Stellarium too. So especially to the people who are new to it, Stellarium is a virtual planetarium software where it's almost photorealistic simulation of the sky as you would see from any point on the surface of the Earth, and it has been released for now 20 years now, and it has been updated quite well. That it's very accurate, reliable, and if you would see some of the things that I'll show today and later you can explore, you would see that it tries to be as close to real observations as possible in terms of the accuracy and the way things work and objects look in the sky. So I have given the link to the download in that abstract. You can easily search online and you should be able to download a version according to the computer that you are using, the operating system you are using. It is advisable that you do a full install on the operating system of your computer rather than use a web version or Android or any of the mobile versions. It may not have all the features as the full-fledged software that you would be using on the computer. If many of you have already downloaded, I mean, some of you can run it in parallel and see, do some of the things as I go along with the demonstration. But if you find it too hard to do with a single screen, then it's okay. You can just follow along here, then try it out. You should have also noticed that there is another link in the abstract to a worksheet that goes along with this. Initially, it was designed so that one doesn't even need any demonstration to go over Stellarium, and they can still learn a lot of different topics just by going through downloading a copy of the Stellarium, running it, and then slowly going over the worksheet and trying to solve all the questions that the worksheet has. It will tell you what options to choose, what are the things that we are trying to find out, and so on. So it is sort of designed so that you don't need any more handholding than it already gives. But in any case, it will only help if I show some of the demonstrations here. Maybe it will be much easier for you to solve solve that worksheet. But I urge you to solve that worksheet in your own time after this session, and come prepared before the next session. Come prepared in the sense, try to solve as many of those questions as possible, so that if you run into any problems or come up with more questions, you can always raise it at that time and we can discuss it. It would be also nice if you come prepared to demonstrate some of the things that you did while solving those questions in the worksheet. It will, be like a little experience for you to demonstrate some of the things that you learned as well. So more on that would be on the next session, which is scheduled for, I think, next Tuesday around the same time. So, so download these two things, the Stellarium software and the worksheet, and you may not need to reference it immediately for this today's session, but you can go over it later. So once you open Stellarium, run it on a computer, most of the time one should not have any problem. It's one of the smoothest software you can just download and run without much problem. It has, I don't think it has a lot of issues running on any platform. So you will. Okay, there's already a question on the chat about the worksheet. If you have the abstract list of, the book of abstracts, you should be able to see there's a link down there. If not, I'll share one later towards the end of the talk. So what are the, if you think about what are the real benefits of using Stellarium, I mean, it shouldn't come as a surprise. Most of you are probably living in densely populated areas where you don't always have good access to the night skies. And it's getting harder and harder with the light pollution. And especially, oftentimes you're also at the mercy of the weather, whether you're able to make long observations of the night sky. So this is a good simulation where anytime you want, you can open it up and make a virtual observation of the night sky, learn a lot about observation astronomy, positional astronomy, and some of the astronomical events as well. It has the added benefits that you can be at any point on the surface of the Earth almost instantaneously by choosing the appropriate location. You can go anywhere in time, backward or forward, for a very long period of time. I think it's close to thousands of years in the past or future, and I'm pretty sure it's fairly accurate, even the positions. And this allows you, I mean, you can either jump to those any other times, and we'll shortly see the demonstration of that, but also you can make the passage of time go faster or slower. You can view the sky as you move really fast along the surface of the simulated surface of the Earth and so on, which has its own benefits to see some of the changes that we could be seeing in the sky and understand why that happens. So on top of that, because it's a simulation, you can have a lot of overlays of various items. For instance, it allows you to mark important points. It allows you to draw grids. It allows you to measure distances, angles. It has a whole suite of applications, plugins that would allow you to do various measurements and so on. So in that sense, I mean, making real observations with the real sky is really great. But this, although it's a simulation, it makes up for it by allowing us to use all these extra features. So once you start up, this is how it will go. It will, show up some default background of the Earth and the sky. And the first few things that you would want to do is pick a location, pick a time. It should have synced to the time of the computer, but location may or may not be synced according to GPS. And then we will have to pick a direction, what we want to observe, and so on. So we'll go through that. If you see on the left bottom corner, there are two panels that are available, one at the bottom and one to the left. And the one on the left has a bunch of menus for choosing, location or viewing options and turning on and off a bunch of things. We'll go through it as and when needed. For now, our purpose is to go to once we fire up Stellarium, we want to go to a particular location, go to a particular time, and start with observation. So you'll see that the first one is for the location window, and here you can either put in your latitude and longitude. That is, you can go to Google Maps to the exact location. If you double click on it, it will tell you what the exact coordinates of that location is. You can put that directly in here, and you can save that as a new location as well. Or if you don't want that much accuracy, you can always go to a city that you live in, search it over here. It's pretty long and extensive list, although of course it won't be complete, but you can always do that. I think it's already set to Pune. Slightly off, I guess. And then your location where you're observing from is set. Once you're done with that, you can fix the date and time. As I said, the time it should have read from the computer clock, and that is why it's already at 4:10. If you see at the bottom panel, it shows the date and time that it's set to, and it also has the passage of time, which is right now running in real time. Okay, there's a chat window in the chat window. Someone has messaged about sharing the session. It's available on YouTube. Uh, we can share the link to the IUCAA channel later. Okay, once you have the the correct location that you want to be in and the time, you can pick the direction you want to look at. Now the thing is, it's right now daytime, so it might be useful to jump to a particular nighttime. So for that, again, like if you want to choose a particular time, you'll have to go to the left-hand menu. And here there's the second option, the date and time window. And if you click on that, you'll see that it's right now set at today's date and time and going in real time. But let's move to, let's say 9 p.m. And you just change the time and it goes directly to how the sky would look if we were looking outside tonight at around 9 p.m. Now you'll see that it tries to simulate a lot of stuff like the atmosphere and the ground, and a lot of things can be about the atmosphere. You can change a few things in this viewing options, sky and viewing options. And if you see, it has an option here for light pollution. So if you want to be ultra realistic about the conditions that are close to your house or location of observation, then you can change it for a highly, densely populated areas. The light pollution is pretty high, so you might have to go to this class that is defined here for um, amount of light pollution of water class 6 or 7. But if you only care about, you want to imagine that the light pollution is not a big issue, which is important for making a lot of sky observations, you may want to turn it down to a small number, let's say 3 or 4, 1, 2. Alternatively, you can go down here in the bottom menu and you can use the atmosphere and turn it off completely. Then it would simply look the way it is supposed to look if there were no atmosphere, scattering due to the atmosphere of the light. And later on, if needed, you can even turn off the ground off from here. But for now, for us to have a good bearing on how these observation is going to correspond to real observations, we'll keep the ground as much as needed. There are a bunch of other animations it does with, meteor showers and satellites. You can turn it off if you would like. If it distracts us, we'll turn it off later. So for now, I'll keep a little bit of refraction, atmosphere. Okay. Now to get a good feel for how to have how this maps on to a real sort of observation you would be doing, you could pick a direction that is accessible to you from your home, let's say from your balcony or your terrace, and you can pick a direction and you can try to do the same in Stellarium. If it's facing south or west or east, you can move it around And then you can try to see if you can see similar stars. You're able to identify the stars that you see here with what you see in the real sky. And that is when it helps to have different levels of light pollution. Because in this, if you turn it off completely, you might see a lot more stars than that are visible in the real sky, and you may have a hard time trying to get this mapping going on. So it might be useful to increase the light pollution. Okay, so you can pick a direction now. Okay, let's just go back a bit and say how we define the directions. Now, no matter where you're standing, except for on the poles of Earth, you will have a well-defined directions of east, west, north, and south. Um, One inaccurate way of trying to figure out your direction would be to use, the rising of the sun, for instance. That is commonly, many people just say it. But the most accurate one would be to figure out north by using the magnetic compass, because we define north and south according to the poles rather than uh, where where the sun rises. As you'll see soon enough, that the sun itself may not rise exactly on the east. So we will start our observations just by looking in the southern direction. You can change the field of view of how much of the sky that is visible by just zooming in or out. Right now, it's the field of view is the actual number is also shown over here in the bottom panel. I try to keep it at comfortable 100, which is close to what you could focus on while you're looking at the sky. Too much or too less, then there are issues trying to keep track of things. But we'll, of course, dynamically move in and out as we need. So once you pick the direction, let's say here south, and you're looking at it, it also helps to have uh, some grids or some lines drawn on. So as I said, we have the cardinal points that is the north. Now the north is behind us, the south is in front of us, or now as I'm moving, the east it will be to our left and the west will be to our right. Yeah. And similarly, you can identify a point that is directly overhead. For this reason, I'll zoom it out a bit so that we can see the entire horizon, which is somewhat unrealistic if we actually try to do it outside. But you can identify a point that is almost near the center of this, disk of the night sky. And that would be our zenith. The zenith would be the point that would be directly overhead for us. Now, once you have identified the cardinal points and you have identified the zenith, you can draw a straight line from the south through the zenith to the north. And that would be your local meridian. Now we'll start with, before that, you can go to the sky and viewing options again. And there is a tab called the markings, where you can turn on a whole bunch of special lines. For now, we'll just turn on the meridian. The first box is to turn on the line itself. The second is to have some markings on it, trying to say what those divisions for angles of it. The third one is to actually put labels to those markings. And now we have the meridian, it starts from the south, goes to the point directly overhead, which is marked as 90 over here, and then connects to the north. Now what we have done is we are just drawing a line locally according to the zenith and our local north and south. You would have realized that north and south itself is a very local concept here. Like, and the zenith will also be very local. So when we draw all these lines, this line, for instance, is what you call as meridian is true for only some of the people on Earth. Especially this one is true only for you as it goes through the meridian. As you go down or up, south or north, east or west, the definition of your meridian is going to change. Since your zenith is changing, so does the meridian. And you can see that already here it's shown with some angles. What we can do is we have defined the meridian. Now we can define the altitude on the meridian. A lot of what I covered today, the positional astronomy stuff and all the sky observations, it closely goes through all the stuff Shomak had taught taught you in his first lecture and possibly the second lecture too. So it's, as long as you understood that, it would be good to put, see that or simulate that in Stellarium over here. So yeah, if you didn't understand some particular topic, let me know. But so what we can do is we not only have this local line called the meridian, which is useful just for making local observations of how the sky changes around you for your location. You can have you can have a grid that is also defined very locally. So that is called the altitude and azimuthal grid. So you can turn on the azimuthal grid over here in the bottom panel. So you can see that the azimuthal grid is defined with the poles at the zenith, and another point that is exactly opposite to your zenith, that will be the point where you're exactly standing, and that is often called the nadir, Nadir. So and since all these are marked with angles, you can see that it's 90 degrees at the zenith, 0 degrees at the horizon, and you can have equal angles as you go up. So similarly, you can have in all the directions, the altitude will be how much of the angle made by any object with the plane of the ground or the horizon. That would be the definition of altitude. Okay, I can answer this message, I guess. So I guess somebody, Kshitij is trying to work along on Stellarium. And his question is, if he clicks accidentally on some point and you get all this bunch of information, I assume that's what he's referring to. How can we get rid of it or reduce it if we don't want that information? Well, if you accidentally click it, try to click somewhere else so that it does not catch on to any other point and it goes off. Sometimes it's harder, sometimes it's easier. But there's also another option in the configuration window on the left. If you go to the configuration window, there is this information tab where once you select an object, it essentially allows you to select if you want all the information on that object or a default set of ones that are still a lot of them, or a very short one with just the name and the position and maybe the brightness, none of them, or you can customize this. As long as you start choosing it, it'll automatically be customized. So that is something you can do so that either you can reduce the number of information that is displayed or get rid of it altogether. Okay. There's a question about how to come back with it, which I don't understand from what. If you can explain what you mean come back from where, then if you mean from selection to off selection, then I just click randomly so that it does not, click on any particular object. Sometimes it works, sometimes it doesn't immediately. Yeah, so just try to click on, I don't have a better answer unless if somebody else has, they can let me know. But these are the only two ways I know. That is, try to select a random empty point in the sky where it does not catch on to another object, or go to that configuration window and turn it off to none so that it does not show any information. Okay, we have turned on the altitude and azimuth grid. We know how to find out the altitudes. We'll come to the importance of that in a minute. And then there is that is one component. No, what we have is a two-dimensional hemisphere, right? That's what the sky looks like to us. So we are mapping a two-dimensional surface, and we need two coordinates. One is the altitude, which is good enough, which is good. The other, what we want to know is in which direction we should be looking. Of course, we can crudely use the directions and say some object is at a particular altitude in the southwest or in the southwest or something like that. But if one wants to be even more accurate, one can use this grid or actually measure an angle. Now here the reference point for what is called the azimuth, which is the direction, is measured from north and it goes towards east. So anything that would be on the meridian towards the northern part of the sky would be at 0 azimuth, and something on the exactly east would be 90 degrees, and then 180 degrees on south, and then back to 270 and 360 or 0 back on north. So this will be a local coordinate system on the sky one can use. It's useful. It's very useful for local observations that one has to make. But this is something you cannot communicate to somebody else working on a different region of the region on Earth, because they'll have their own meridian. If you say something is 30 degrees above the horizon over here, it very likely won't be at the same altitude over there. Similarly, for the direction, you can say something is 180-degree azimuth, which is in the southern towards south for you. But if they are, let's say, in the southern hemisphere, it may very well be north for them. But still, it has its use for just local observations, and for observatories, one can use it, and so on. I will turn off this, I will turn it on later. Now we'll try to go and see how some of the motions that happen over small time scales. So to increase the speed at which the simulation runs, or to increase the pace of passage of time, you can use the controls over here. There are 4 of them. Right now there's like a play button over here, which is highlighted, which means it's running on real time. There's a rewind and a fast forward symbols. I assume that's what these symbols are called. But let's say we want to fast forward things. On one click, you won't see much of a difference visually in the sky, but you can see the seconds. Seconds are running much faster than earlier. A little more, and you can barely try to see the difference. You can see the stars are moving slightly faster, and I think it's about a minute a second. The rate at which time is passing is about a minute a second. And as you go on gradually increasing it, you can see that the sky moves much faster. I hope the video is not too choppy. Depending on your connection, it may get choppy. I don't think I can do much about it, except try not to increase the speed too much. But what you will see is the first basic motion that we're going to focus on. Okay, now is a good time to turn off the atmosphere completely so that we are not affected by the sun popping up. Now what you see is the sky, okay, what do you see? You see that a lot of these astronomical objects are rising not exactly from the east, but from the entire eastern half of the horizon. So you can see that there are objects that are even rising very close to the sun, to your south, or somewhere in the southeast. There are some of them obviously rising in the east, but not all of them, and there are quite a few in the north as well. So uniformly there are things that are rising up from the eastern half of your horizon. And then what do? They transit on the meridian. So we have drawn this line, the meridian, which is the path, again, a line joining your local south, north through the point called the zenith. And it transits, moves on to the western half, and they all uniformly set in the west, but the western half of the horizon. Not all of them are exactly on west, some of them southwest, some of them close to south. Now, you must have recognized, all of you, that this is due to the rotation of the Earth, right? So in the course, if you notice, we have gone past, I think, about 2 rotations. Today is the 17th, and right now it's showing this is 19th. So what is happening is uniformly the objects rise, transit the meridian. By transit, I just mean they cross the meridian and then set. The meridian is also important because this is the point, or the line along which the objects will reach their maximum altitude, the altitude that we described as the height above the surface of the Earth. And you can see that no matter where it's rising, even if it's very close to the direction of south, we can, follow an object, not that one, this one, let's say. It rises, and if you see the information that is given on the left, you can see that the altitude as azimuth are changing. But you'll notice that no matter which one you choose, it will go to the highest altitude as it transits the meridian, and then it uniformly decreases, and then it sets. Okay, there's a question about how did we select the meridian. So meridian is a local concept. You pick the cardinal directions, you determine where your south is, your north is, and that should be fairly straightforward. And then the third point you need is the point directly overhead. That should also be, I mean, in a real situation, that should also be possible to, fairly accurately, if not absolutely accurately. So it would be a point that wherever you're standing directly overhead. So that would be the zenith. So you would draw a line from the south to the zenith to the north, and that is your meridian. Lakshmi Raja, I hope that's clear to you. Yeah, there are a whole bunch of satellites. I mean, satellites, they are giving accurate locations. There's a question about does it show satellites? If you notice, sometimes when I clicked on it, it just started moving in a random direction and pretty fast, and those are most likely satellites. If it gets too pesky, I just turn it off. You can turn off the satellites over here. You can see a satellite-like icon, and it won't bother you. And then there's a toggle for meteor showers. Meteor showers, obviously, I think they are all simulated in the sense they are randomly generated. They're not tracking any real-time meteor showers. You can turn that off if that distracts you too. We have turned off the satellites. Okay, now we'll go back. Okay, one of the things you'll see is that whenever you run these simulations, if you go real fast in the future or past, and you're sort of way past the time point from which you started, you can come back to it very fast by choosing this, I don't know, sand clock-like symbol that is just next to the play icon. So if you do that, it will automatically come to today's time and today's time. Okay, there's another question. Okay, I think we'll come to that. There was a question about using Polestar. We'll get to that in a bit, so let's not jump there. So what you saw was the one of the basic motion that you would see at the lowest time scales uniformly in the sky, which is the uniform motion of things rising from the east and setting in the west, apparently rising in the east and apparently setting in the west due to the rotation of the Earth. As it does, it transits. Now, the same thing is true for the solar system objects as well. The moon will do the same because it's all due to Earth's rotation. Now, we'll focus a bit on the sun. The sun, background stars are really far away. Their motions are not going to change for the timescales of days or even years. So we need not worry about them. We know that they uniformly rise, uniformly set, and that's all they do in these timescales. Only maybe in thousands of years, their actual positions might change to the accuracy that's needed for making simple sky observations. But sun is something that is quite important to us, and we would like to see how that changes in the sky. The first impression should be that, as you see, it seems to follow along with the stars. It just seems to do the same thing. It rises from the east, not exactly from the east. If you go back a bit, let's make it go. Yeah, make it go. So it's summer months, so it's fairly close to the east. But you can see that it's not exactly from the east. It's rather between northeast and east. That's where the sun rises. Now we let it go forward a little faster. So what it does, it just like everything else, rises from the east, and it will go towards transiting the meridian. It will stop. Now again, now we'll come to how the position of this, where exactly the sun rises, will also keep changing depending on the time of the year you're observing. Okay, right now we have the sun at the very close to the meridian. It's useful for our civilian purposes, generally biological purposes, to have the sun have our time defined according to the sun. We would want our daytimes to have the most sun consistently throughout the year, and the night times to have darkness. It just helps with our biological clocks. So what we do is actually define the time, our daily times, according to the sun, position of the sun. Now you'll notice that just if you look at the motion of the sun over a few days or over just one day, you would see it just moving just like any other stars. But even then, before we come to how it moves with respect to the stars, we'll see that it's a useful concept to define our noon, that is middle of the day, according to when sun is the highest. And as I said, any object that transits the meridian is at the highest altitude for that particular day. The local solar time is defined according to transit of the sun. When I say transit of meridian. That's a very good prescription that works. That's how you would define an apparent solar time according to that. But it can cause a lot of problems because, as I said, the meridian changes as soon as you move from this location. Your meridian is slightly different, and it changes quite significantly very soon as you move away, crossing the longitudes. So what we have done for ease of trade, commerce, and everything is that divided things into time zones rather than use the meridian at every single point on Earth. We have taken regions of longitude and then defined a common time zone, defined a mean longitude within that time zone, and then the solar time is defined according to that longitude. So for us, I think it crosses somewhere near Jharkhand, Uttar Pradesh, and so on. And since right now I'm showing a simulation that is close to a position in Maharashtra, if you would actually see the time, it won't be 12, rather it's close to 12:30. And part of this difference is due to this definition of time zones, and that time zone, that particular time for a particular region defined according to a single longitude or single meridian, which is somewhere in the mean location for that zone. And since since Pune is slightly at the edge, it is about half an hour off. There's another little difference due to the eccentricity of the orbit of the Earth around the Sun, that its apparent motion changes laterally. So that's also figured in. But the major effect is due to the time zone. But this is a good one. Okay. So another thing one can do is try to see, as I said, the path of the sun looks like it rises close to the east and transits right now here. But you saw that the actual place where it rose was between northeast and east. And as you go to different months of the year, you'll notice that the where the sun transits on the meridian also keeps changing. So right now it's in May, that is 5 as it's shown. So what you can do is you can go to this date and time window, you can select a particular date or month, and you can use the arrow keys to quickly jump through time. So with just one click, I could just go to June, and you can see that the sun has gone even higher up, or rather highest would be 90 degrees. So you should say that it has gone the other direction, slightly down. It was, let's see, in May, it was very close to 90. That is why we had like a zero shadow day just a couple of days back. And as it goes to June, it will go slightly lower, but compared to its altitude from the south, you could say it as higher, I suppose. But the effect of this is that in the summer months, the length of the days are longer compared to the winter months. Now we'll move to the winter months to show how high the sun goes. So this June, then by July it tries to come back towards 90. Then August it goes below 90. That is the maximum height it's going to reach. Let's say in August, September, October, November. You can see this is in on a day in the month of November, the highest it's going to be in the sky is less than 60 degrees. This is in contrast to how high it gets during the summer months in May or June, which is close to 90. And if you would want to see the motion of the sun itself, where it now rises and sets, let's first yeah. So it will rise now, and you'll see that we saw in May it was rising between northeast and east, but right now it's from between east and southeast. So the direction in which the sun rises itself changes, and the maximum height it goes changes, and then it transits. And you can see that this arc that it makes from between southeast and south southeast, transiting less than 60 degrees altitude, and then setting uh, west southwest is a smaller arc compared to, let's say, in May. Let's go to May very quickly. Yeah. In May, again, it rises somewhere past east. It may not be very obvious, but it takes a very long arc, goes very high up in the sky, close to 90, and then sets. That's why the summer days are longer. Now we'll focus on the motion of the sun itself. Now there's a little activity in the worksheet about trying to see how long it takes for the sun to come back to the meridian. As I said, because of our definition, it will be close to a day, 24 hours. But you can do the same thing with the star, and you'll see that the length of time it takes for the star to come back to the meridian, for instance, will change. And that is the first hint that, the reason for that is we define the time according to the sun, but we are also moving around the sun, which means the position of the stars or the position of the sun with respect to stars keep changing very slowly with time, but nevertheless it does. Now we'll focus a little bit more on how the motion of the sun changes. For that, it's useful to turn on another line called the ecliptic. And on the ecliptic line, the angles and markings, even though they may not be extremely important. Now, ecliptic, from the name itself, you must have heard it by now. It is also the plane on which the solar system planets are revolving. So there is a definite plane on which all the solar system's objects go about the sun, and that is called the ecliptic plane. Now, this ecliptic line is essentially the two-dimensional projection of that plane onto the sky. So in the local sky, or generally on the celestial sphere, it will cut along a line, and that is the ecliptic line. And as you can see, you can see already some of the planets along the ecliptic line. That is because you'll always see, if you see planets, it's very likely going to be pretty much on a particular line, and that is the ecliptic line because all of them inhabit in the same ecliptic plane around the sun. Now, although the Earth is moving around the sun a lot more than the sun is moving about a little barycentric point, but since our observation is with respect to a point on the Earth, we would see the Earth as static and the sun to be moving around the Earth. It's just relative motion. And since we are on the ecliptic, you will see the sun to be apparently moving on the ecliptic. So for that, let's go a bit close. Okay. Now, another thing to make it obvious, so we would want to see how it moves with respect to the stars. Now, people in ancient times have come up with nice little diagrams to connect various stars and make shapes out in the sky. and that often proves quite useful for making very simple sky observations, because you can keep track of various solar system objects with respect to these background constellations or stars. Even though stars might be a bit hard, that's why the constellations help. So we'll turn that on. You can turn on the constellations using the options here in the bottom menu. The one on the left is for constellation lines. You can turn on the labels and then an R2 if you want. Additionally, you can go to the sky and viewing option, and under star lore, you can turn on the boundaries. This will also help you keep track of, it is very faint over here, but you can keep track of approximately which constellation a particular object is in. So what we want to see is track the position of the sun, let's say, over longer periods of time now. We have seen throughout the day it just rises and sets, staying sort of on a point on the ecliptic. Now, if you want to focus on a particular object and then see its motion relative to other objects, it's usually helpful to use this option of centering on a selected object. What it does is it always try to keep the field of view centered on the object of interest. Otherwise, things keep on changing in the sky. It's hard to keep track of both the rotation and the revolution that we're going to see in a minute. It's also useful if you're going for timescales larger than the rotation of Earth. It's also useful to turn off ground temporarily so that it doesn't come and obscure from time to time. Or in this case, it may not matter, because uh, if we are going to keep the time of observation the same, then as long as it's in the sky on a particular day, if you go and observe the sun again on a particular day, on a different day at the same time, you're going to have it in the sky. So we can keep that on. So we have the sun, if you see, in front of the constellation Taurus, about close to 60 degrees on the ecliptic. I'll come to defining the angles on the ecliptic as well. But for now, we'll use the date and time window and then go forward, jump forward in days, keeping the time the same, so that every step is a step in a 24-hour step. So you'd see that as soon as you go one, you can already see the motion that the sun apparently moves on the ecliptic. So this is what happened, and it's going against these constellations, especially if you consider these stars, since they are very far away. You can assume that as a uniform background that does not change for very long periods of time. You can measure the motions of sun, and you can also see the planets that are coming up here, or they'll come on as we move on, that they all move with respect to these stars. And this is, as you would realize, just the motion of the earth as it goes around the sun. From the viewpoint of Earth, it is relative motion of the sun. So what the sun will do is, over the course of a year, it will keep on moving through constellations. Um as you also saw in the local sky between summer and winter, you see that it comes up at various different altitudes. That's essentially because its position on the ecliptic with respect to the stars are changing. Okay, somehow move the center away. So let's keep the sun in the center. And you'll see that it moves. We'll start with, let's say, we'll do one thing. We'll go to close to the meridian. And we can see how it changes. So you know that, okay, it might be slightly disorienting because I'm zoomed in quite a bit. But you can see that right now it's almost transiting. You can just go like a day ahead in time. Okay, we'll do closer. So as I jump in time by about 1 day, you can see how the position of the stars, the background stars, change. So for instance, okay, this is closest to the meridian. So the time is pretty much the same. We define the time according to the sun, and we jump instantly on time. So the sun would be, still in the same place, except for the few seconds that it has moved. But you can see the star has moved more than it was in the previous day at the same time. So okay, we can probably even stop time. So we pause time and we come back uh, to the same time the next day, and you can see the star. So what the sun has done is sun has moved to the right on the screen. The right is the west. So over time it has gone to the west as it sets, then goes back, turns back and comes towards the east, rises in the east and comes back to the meridian. That is how we have defined as 1 day or 24 hours. And that is what the sun has done. But what the star that we are keeping track of has done is that in the same time it has gone around, made one full rotation and gone a little bit even ahead. That's the small effect of the earth moving around the sun during the course of a day. That is why the apparent position of the star has changed. And if you go even one more day, it keeps on changing. The sun does not change much. There is a very little change, and that, as I explained, is due to the eccentricity in the orbit. Yeah. So the sidereal day, I can see that somebody had asked a question about sidereal day. If we were to actually define a day according to when, let's say you, instead of the sun, you want to record the time of one complete rotation of the Earth. With respect to the non-changing stars, you would pick a star, you would see when it transits. Then next day, if you come back and see exactly when the same star transits, that would define as a rotation of the Earth, right? And that would be the sidereal day. It's defined according to the stars, not the sun. But it will have this problem that, let's say we define 24 hours according to this absolute rotation, then the sun is going to be later and later or earlier. Yeah, the sun is going to, over time, you'll see that in after 6 months, the star will again transit, but the sun would just be rising at that time. Now, that is something we don't want. We don't want the middle of the day to be the time when the sun rises. So that is why we avoid that particular way of keeping time. Okay. Oh, okay. I'll quickly move on to the another very important coordinate system, that is the absolute coordinate system of equatorial coordinate system. So we looked at the south. Now let's go and look in the northern direction and let time go. So if we increase the passage of time, you see something interesting in the north. This is again, you would have noticed this in the lecture, yesterday's lecture, that we have a point on the north. I mean, we are in the northern hemisphere. So we have a point on the northern part of the sky where it seems that uh, there's a point on the sky which doesn't seem to rise or set. It just stays in the same spot. And the stars and constellations that are closest to that particular point seem to just rotate about that point. Now, this would be obvious again, just like rising and setting of the sun in the time scale of a day, is that this is due to the rotation of the Earth, and this point is static because this is the point through which the north pole of the rotational north pole of the Earth passes. So the way to imagine this is to think of a celestial sphere. If you are new to this concept, is just imaginary sphere at, let's say, very large distance, say close to it's at a very large distance concentric to Earth. So you have this Earth, and you have a very large sphere concentric to Earth around it, and that would be a celestial sphere. And all the stars and even all the objects that we see in the sky are assumed to be on that sphere. Now, if the Earth rotates, there will be 2 points. The Earth's rotational axis will cut the celestial sphere at 2 points, the northern and the southern point, which are called the North Celestial Pole and the South Celestial Pole. And these points you can imagine for rotations, these points will remain static no matter what. And from the viewpoint of the Earth, let's say Earth is rotating, but we are standing on Earth and imagining Earth to be static. Then we'll see relative motion of the celestial sphere around us, but these North Celestial Pole point and the South Celestial Pole point won't rotate. So if you see in the northern region of the sky, if you do it for longer observations, actual observations, you'll see that the stars will go about a particular point, the north celestial pole point. And in the northern hemisphere, there is a star that is very close to the north celestial pole point called Polaris. This is the star over here. You can use constellations to, find the location of the star. One usually uses Dipper, the Big Dipper, for instance. This is the Big Dipper, the 7 stars of the Big Dipper. It's an asterism. The asterism is part of a constellation called the Ursa Major, but you just need to consider this, sort of what do you call that? A bowl-shaped part of the Dipper, and the 2 bright stars towards the pole end of it rather than the handle end of it. You can extend it towards the north. I mean, it goes about it. So all you have to do is, try to take these 2 stars and go about 4 times the distance between the 2 stars up above the Dipper. And you'll see that in this region, generally, there's only 1 bright star. Right now, we have turned off the atmosphere. Oh, okay. Jump to night. So with light pollution, it will help to locate the Polaris much better, because in this region as long as you know approximately where the northern region of the sky is, you can see that Dipper has moved over here for that particular time, and you can use these 2 stars and locate the northern celestial pole point location, and in that the brightest star is Polaris. It's part of another Dipper-like asterism called the Little Dipper. And the stars and constellations that just go about. So as you must have noticed, there are these stars and constellations near near Polaris. They won't set or rise. The ones that lie between the angle, between the altitude of Polaris and the horizon. These would be the stars and constellations that never set or rise. Now, to have a better understanding of, to people who are new to this, sometimes there is some confusion to understand what these points are and how it relates to locally where you're standing. So it is often useful to think of other location on Earth and then try to imagine where this point would be. So for instance, you can imagine you are at the North Pole of Earth, and you want to observe Polaris. Where do you think it will be? Now, the worksheets will ask you to essentially answer that. It's best to imagine the celestial sphere and come up with an answer. But you can obviously try to, simulate it by moving your coordinates to somewhere near the North Pole and actually seeing it, what happens. Similarly, you can do to the South Pole, and so on. Now, as we said, we are using the rotation of the Earth to define, and because of the rotation of Earth, we have this obvious points that are going to remain static for a very long time, and we can define these as reference points. Now, similarly, we can use the Earth's equator as a reference line altogether. Now, let's turn it on using the sky and viewing options, markings, and equator. Now, if you have the concept right in your mind, then you'll see that, okay, turn down constellation so that it's not too messy. Maybe no. I'll turn off the ecliptic for now. So since since we know we realize that we are looking at the celestial sphere, which is apparently moving because of rotation of the Earth. We recognize that there are 2 points, the North Celestial Pole point and South Celestial Pole point, which are extensions of the North Pole and the South Pole on Earth onto the sky. Similarly, there's the equator, which is a well-defined line all around Earth, 90 degrees from the pole. Now, this can be extended onto the sky, and that is the line, the blue line that you see on the top over here. Now, this is the celestial equator because it has been Earth's equator has been extended to the sky. Now, again, you can do the same, imaginary exercise of imagining if you are standing exactly on the equator, where exactly this celestial equator would be on your sky. Now, that is something you can figure out. But for our, since we are and as we go north, the equator will appear to go to move south with respect to where it was if you're standing on equator. And you can see that for our location, it is in the southern sky. It starts exactly on the east as you would expect, and then it has a particular altitude. Now this is related to the latitude of your location. Again, that is something, by doing that exercise, you'll figure out what the relation is, and then it connects to the west. Okay. There's a question about the 3 options in the sky and view options for turning on these lights. So you'll see that for all of these. So the thing is, if you hover over it, it should show you that the first one is to actually show the line. The second one is to show these markings. You can see that it's the line is graduated to show degrees. And the third one is to show the labels. So if you turn it off, there will be those graduations, there will be these lines, but not the label. And similarly, you can turn this off and there'll be no label. The left one needs to be turned on for the right one to work. So if you just remove the line altogether, nothing will show up. But that's what these 3 boxes are. Depending on how clearly you want it, you can turn that on. So you can see that the relative position of this doesn't matter, doesn't change, because again, just like the pole points, these are according to points defined symmetrically on Earth to, according to the poles, which are along which things are rotating. So the celestial equator also does not change relative to height and so on. Now, using these 2 points, you can, you can use this coordinate system. That's the equatorial coordinate system. And just like we have longitude, this is essentially like longitudes and latitudes, except they are all projected onto the sky. However, the 0 of it is defined according to the position of the sun. So I'll turn on the ecliptic real quick. And you'll see that the ecliptic is not parallel to this equator line. So the equator line, if you see, is the 0 degree line here. Of course, all these lines of, lines of equal right ascension are parallel to it. But you'll see that this red line, which is the ecliptic, is, cuts across all these lines. And that's because of the inclination of the Earth. The Earth, as it goes around the sun, is inclined with respect to that plane. So when we define a coordinate system that is according to the rotation of the Earth, that particular plane, which is the ecliptic plane, will be inclined with respect to it, just because of the inclination of the Earth's axis. Now, because of this, we define right ascension and declination on this equatorial grid. And we define the 0 according to when the sun is on what is called the ascending node. That is, over the course of the year, the sun is going to move on the ecliptic, but as it moves through the course of the year, it will go to, it will go above the equatorial, the celestial equator in the spring. And as it crosses the equator, this is the equator line, the 0 degree. That is where we'll define the 0 of right ascension. And it goes, it increases towards the east or left. and comes back to 24 hours or 360 degrees. And similarly, since we have this equator, we can define declinations, essentially angles away from the equator, north or south, according to, let's say, 10 degrees north, 10 degrees south, and so on. Now you can see that for, most of these motions we are interested in, of the scales of the days and even years, the stars won't move with respect to this grid, unlike the case where we had an alt-azimuth grid. So this is very useful to assign uh, permanent locations or permanent coordinates for different objects in the sky and communicate it to people observing from other places on Earth. So this is the RA and DEC locations that you see for defined for objects. Now, there are other motions that happen at large time scales, nutation of uh, precession and nutation due to the rotation of the Earth's, the axis of the Earth also nutates and precesses, because of which this definition of zero changes over thousands of years time scale. That is why one has to redefine it for epochs of time. 1950 one was defined. Currently, we're using something called J2000. So essentially, it is defined according to where the sun's ascending node was in the year 2000 and so on. But for daily and yearly motions, one doesn't have to worry too much about it. Okay, so I think I'll stop here. It should. I try to give a good demo of yeah, sort of the motions that one sees in the sky. In the process, I hope I showed a whole bunch of features you can use to increase or decrease the passage of time, and jump to various times, turn on various threads, all these features that you would need to solve some of the problems in that worksheet. Hope it helps. We can take a few questions, I think. So I think most of the questions in the chat I have already answered in between. Yeah, the last question, which was about J2000, is, as I said, there are other motions that happen at much longer time scale. So uh, in different epochs, you will have to redefine where exactly you're defining your zero. Your ascending node keeps changing a bit after many years. So one does that according to a particular day and then keeps it same for, let's say, tens of years at least. And that is what it allows you to change. Sorry, not this. Sky viewing options. Yeah, there's a J2000. And equator update would be today. If you wanted to see where exactly the ascending node is today and want to define the coordinates according to that, then you would turn this on. But better stick to J2000. That is pretty standard what is used. And if you see publications, people will give coordinates of various objects. One has to essentially mention which epoch one is referring to, and nowadays most of them refer to J2000. Okay, some other questions. Why does the ground appear concave up? I think it's a question of projection. You can choose the sort of projection you want to see. I forgot where exactly that projection was. I think it is sky and view options. Maybe not. Oh yeah, perspective. I don't know. This is closer to how you would actually see, possibly. But then, yeah, we are trying to project that sort of two-dimensional hemispherical volume onto a two-dimensional screen. So I think that is why some distortions are there. You can choose, as I showed, you can choose different projections if you would like. I think this one works fine if you just ignore this concaving up of the ground. Okay, what's next? Where do we get the worksheets? Uh, I assume all of you have access to the book of abstracts. There is a link right there. Let me see if I can get share a link right now. Or one of you can, if you can find that link, can you just put it in the chat window so that others who couldn't find that link can get it? Just share it with everyone, the chat. What's the next one? How far can we see zooming in? So you would see that you would be surprised. It's quite good. You can zoom quite well, and they have done a wonderful job of putting pictures from the Hubble Space Telescope for various objects. Surprisingly, I'm not finding anything in this field of view. Otherwise, I usually run into some cluster or Antares is in like a nebulous region. So they look very photorealistic. So you can do a control F and search for things too. So let's say Saturn. So it will look just like a point depending on the zoom, and you can go zooming in further, and you'll see it even has accurate location of the moons around it, and a photorealistic image of Saturn, and possibly even its inclination and everything. So Ryan Nebula, for instance, it went into the ground. So you can see, you can zoom in pretty well. Right now it's a field of view of just 2 degrees. So in that sense, it's pretty neat. Okay, what's the next question? Can we make Deneb as a pole star, as we said that after 10,000 years it's going to be a pole star? Well, it's not our choice to make what a pole star is. It just happens. Okay, first of all, we shouldn't even be focusing on a star. We just need to know what the north celestial pole point is, and it may not be a star. For instance, if you, as part of the activity, you will go to the southern hemisphere, a point on the southern hemisphere, and try to look for a point which doesn't seem to rotate or move at all, and that would be the south celestial pole point, and there's no bright star close to it. So all we have to focus is on that point, and very soon Polaris is going to shift away from that point, and we won't be left with any star near there. So it's not a question about what we want. It's for us to decide which star we want to use as a pole star. So this is in response to a question where someone asks whether we can make Deneb as our pole star. We may not, unless it is coincident with a north celestial pole point. I don't know whether Deneb is going to be. I thought it was Vega. I think Vega is eventually the pole will shift towards Vega. Information about azimuthal and equatorial gate. Intersection of azimuthal and the intersect. So there's a question about, can we get any information by intersection of azimuthal and equatorial grid? The answer is they are defined for totally different purposes. One is for just making local observations about how high something is up in the sky with respect to the horizon or which direction it is. And the other is absolute system, where it is according to, it takes into account the rotation of the Earth, and the revolution around the sun is not that big of a change for the position of the stars. So it works very well in defining an absolute coordinate system. So to combine these two, you won't gain anything. It will only confuse. So depending on your use, if you're making a local observation, you can use alt-azimuth. If you want to communicate that to somebody, use the equatorial coordinate system. Why there is Sagittarius A and B? So usually, often there are the convention is that if you see, let's say, a bunch of objects, they want to group it and classify it. Let's say even bright stars that are form a part of a cluster. Let's say people tend to name it as alpha, beta, gamma according to brightness. I don't exactly know. There is a Sagittarius B. Sagittarius A star is what we call the central black hole that is in our Milky Way. But I frankly don't know the answer to why there is Sagittarius A and B, and whether there is a Sagittarius B. I can get back to you. Can you suggest some work on history of Indian astronomy and how they explored? Sadly, I don't know. good references. Just start with Wikipedia. That's what I would do. It has a lot of information and references right there. That would be my bet for starting to look into it. So there's another thing about in sky and viewing options. Although it's not very well fleshed out, you can change the star lore. By default, we have these constellations that are the Western defined ones, names and so on. But you can choose a whole lot of other cultures as well. Not all of them look very dramatic, or maybe even incomplete. I'm not sure what is the reason, but you can explore these. You can see cluster names by turning deep space object on. Yes, that's true. I thought it must be on. Okay, there's something called deep space objects over here. You can turn it on. Okay, there are a lot more. These NGC objects from the NGC catalog or NESI catalog, all these things, you can turn it on. It gets a bit messy to check out do other activities, but if you are hunting for objects, then you may as well turn this on. And you can always do Control F and search for an object here by position, by name. Okay, thanks for sharing the links, although all the links are shared to me. So I'll share the link to where that activity worksheet is. If you don't already have that, please take a note right now before the chat closes. Okay, so that's about it. I think the questions and okay, then at the end there's a question about organization in India which helps people do stargazing in clear skies. I don't know. Atharva, do you have any idea about this? Yeah, okay. There is a question that I think it came directly to me. It's about organizations in India which help do stargazing in clear skies. I mean, SIPOP itself does it, right? On Fridays. Go ahead.
I can share a link of all the organizations I know.
Great.
We have compiled a list of these organizations in India where you can do stargazing. So let me just paste the link in the chat window right away.
Right. Or you can later put it on Slack too.
Yeah, that works.
Yeah. So if you get it right now, you can put it. That's fine. And why there is a star against Sagittarius A star? Again, I don't know about it. Check Google, I would say. Frankly, I don't know the reason why there is a star against Sagittarius A star. Okay, yeah, well past the time that was allocated to us. If there are no other questions, I'll go through the form, the questions you may have submitted through that form later during the second session. And as you go on working with these worksheets, you'll have a lot more questions, I'm sure. You can put that questions on there. Refresher course participants, you can, of course, put it in one of the Moodle forums and discuss among yourself and get the answers too. But the ones that are not answered, or if a lot of people are struggling with something, I'll address it in the next session. You can enter those questions there. For now, I think we'll stop here. Thanks everyone for joining. Santosh? Okay.
I have paused the recording right now.
Okay, yeah, I wanted to stop it, but then I wasn't sure it's gonna cause a problem with the stream. Anyway, I think Santosh can end the session. I don't hear him. Maybe he's not around. I can only leave. I cannot end the session.